which can be said as A2 omega n square phi n transpose k phi n can be actually said as omega n square m n by standard derivation. Hence, A2 omega n square m n, which is A2 omega n 4 m n. So, substituting for L equals 0, 1 and 2 in equation 10, substituting the above in equation 10, we get C n will be summation of L equals 0 n minus 1. You can see here equation 10 C n L equals 0 n minus 1 phi n n. So, we have worked out phi n transpose C 0 C 1 C 2, we have to do the summation, right. So, it is going to be A L omega n 2 L of m n, equation 11. Now, damping ratio zeta n is given by C n by 2 n omega n. So, zeta n is now going to be half of summation of L equals 0 to n minus 1 A L omega n 2 L minus 1, equation 12. So, it is interesting to know that the coefficients of damping matrix, that is A L, can be determined from various damping ratios specified for any J modes. This can be done by solving J algebraic equations of equation 12. So, for unknowns of A L, for L equals 0, 1 etcetera till j minus 1, this can be done. The above can be done. Okay? I do not think there is any confusion in this. Once the damping coefficients A L are determined for J modes, then the damping matrix C n is known from equation 11. Okay. And damping ratios zeta n are given by equation 12. There are some important observations of Kage series. The algebraic sum of the equation, that is equation 12, algebraic sum of equation 12 are numerically ill conditioned, because the coefficients omega n minus 1, omega n minus 2, etcetera, omega n cube, omega n phi can differ in various order of magnitudes. Now, how to address this issue? If more than 2 terms are included in Kage series, C becomes a full matrix. Even for K being a banded matrix and M being diagonal because mass is dumped. So, what is the consequence of this? The consequence is this increases the computational cost and time, because the matrix now becomes a full matrix, especially when applied to large systems. Let us take an example problem. The same case what we did. Let us say this is M1, M2, M3, M1, M2 and M3 or M, let us say it is 3500 kg. This is K1, this is 1.5 K1, this is 2 K1 and K1 is simply K, which is 1500 kilonewton per meter. And let us say assume zeta 5% in all modes. So, using Kage series, let us evaluate. So, evaluate classical damping, using Kage series. Okay, that is the question asked. We all know that omega 1 for this problem is 11.8 radians per second, omega 2 is 29.27 and omega 3 is 44.778 and the corresponding mode shapes also are known to us. Phi 1 is 1.68 and 0.32, phi 2 is 1, minus 1 and minus 1 and phi 3 is 1, minus 3.68 and plus 4.68. This we already know. So, we know that 2 zeta n is equal to A 0 by omega n plus A 1 omega n plus A 2 omega n cube. This is actually the value what we have from this equation. Okay. So, 2 zeta n is, we are taking 3 series 0, 1 and 2. So, A 0, A 1 and A 2. So, if it is 0, L is 0, this becomes 1 by omega n, that is the term what we are getting here. Similarly, if this is 1, so zeta 1, A 1, this becomes omega n, that is what we are getting here, the second term. And similarly, if this is 2. So, 1 by 2 a 2 and this is going to be omega n cube, that is what we are getting here. So, 3 terms. Okay. So, very interesting. 2, I am assuming damping ratio same in all the modes, classical damping, which is expressed as in matrix form 1 by 11.8, that is my omega 1, 1 by 29.27 omega 2, 1 by 44.778, then omega 1, omega 2 and omega 3, then omega 1 cube, omega 2 cube and omega 3 cube of a 0, a 1 and a 2. I can convert the above equation into a matrix form as given below. Now, I call this matrix as A. Find A inverse. Okay. So, that will give you the coefficient matrix A 0, A 1 and A 2. Once you know A 0, A 1 and A 2, one can find C as given by Kage series. Which actually equal to A 0 m plus A 1 k plus A 2 of k m inverse k. This can be easily solved and found. Let us take a computer program of this. So, this is a program which is showing you the Kage damping. We have to enter the degrees of freedom, okay, enter the degrees of freedom, give the mass matrix, give the stiffness matrix, assume damping same in all modes, classical damping. Then of course, eigenvalues and eigenvectors are determined, we already have the answers with us, get the modal matrix, then find out the damping constants and then find the C matrix. The program is actually continuing from here and to here, okay, it is continuously here and then print. So, mass matrix is input, stiffness, frequencies, corresponding mode shape and the damping matrix. You will notice that the damping matrix obtained for all the 3 degrees including mode 1, 2 and 3 is marginally different from what you obtained from Rayleigh damping in the last lecture. So, friends, let us quick at the summary of this lecture. In this lecture, we learned the Kage series of estimating classical damping matrix. We have also seen the limitations or observations of using the Kage series. We have done a numerical example. We also give the computer coding to solve the problem and we compared the answers and validated. We have also seen the damping matrix obtained by Rayleigh and the damping matrix obtained by Kage are more or less similar for zeta equals 5% in all 3 modes. I hope you have followed this lecture. You will attempt to solve this problem completely using a computer program, compare the answers for other application problems and let me know if you have any difficulties. Thank you very much.